Okay, so we will proceed in proof 6. We will prove the polynomial approximation of any function. So now that our through differentiation, if we see the differentiation, then our formula is ready. If I have a function fx, if I have a function fx, then if I calculate all the derivatives, df by dx, d2f by dx square, d3, okay, so d3f by dx cube, d4x by dx4. So if we have all the partial derivative that is calculated, all the partial derivative that is calculated, so if I have a function fx and I have another function gx, fx gx, from fx I calculate all the derivatives, df by dx, d2f by dx square, d3f by dx cube, dnx by dxn, and give it to gx, from fx to gx. Now gx, so gx is called polynomial approximation of fx. If fx is a function, inside that there can be polynomial, monomial, binomial, sinusoidal, exponential. So many functions are there inside fx. If I just calculate all the derivatives and those derivatives are fed to gx, now gx can recreate fx by dfx by dx into x plus d2f by dx square into x square by 2 plus d3f by dx cube into x to the power 3 by factorial of 3, d4x by dx4 x to the power 4 by factorial of 4, dxn by dxn x to the power n by factorial of n. Okay, if that is the case, then gx is polynomial approximation of fx. Fx is in term of x to the power so many, sin x, exponential, logarithmic, and cos x, and so many functions. So fx, from fx, I fetch all the derivatives and I create gx with only polynomial, x to the power 1, x to the power 2, x to the power 3, and x to the power n, where coefficient of x to the power 1 is df by dx, x to the power n coefficient is dxn by dxn, dxn by dx to the power n. Okay, so I have polynomial expression as gx that is replica of fx, where fx is anything that is function of x. This is what we saw. How we proved it, that one by one we took. We consider fx as a function of monomial. Then exact I can create a monomial, recreate monomial as approximation or exact, like dfx by dx, means differentiation of f with x, df by dx into x, then exact replica. If it is power of 3, only power of 3, if fx is a polynomial, trinomial of power of 3 only, like k x to the power 3, exactly I can replicate as d3f by dx cube into x to the power 3 divided by factorial of 3. If it is only one power, that is k x to the power n, then here dnx by dxn into x to the power n divided by factorial of n. If f is combination of all the polynomial, then gx is also combination of all the polynomial. So we just add it and it comes as fx x into I'm sorry, f dash f f dash x, df by dx, df by dx into x plus d2f by dx square into x square by factorial of 2 plus d3fx by dx into x to the power 3 factorial by divided by factorial of 3 plus dnx by dxn into x to the power n divided by factorial of n. So fx is polynomial of combination of all polynomials. The gx is also combination of all polynomials. We call it gx is polynomial replica of fx or polynomial approximation of fx. Now fx is combination of all polynomial plus any function. So fx is a black box. If fx is a black box, then gx is same thing what we described. So only thing is from fx I need to fetch all the derivatives. Now what about then what we used this dx for? Then if I do the derivative of fx, if I differentiate fx and whatever comes as differentiation of fx, then if I set it to 0, df by dx, if I set it to 0, then whatever x I get at that x, df by dx equal to 0. df by dx is another function of x. If I set it to 0, I get some x value. We call it x0. At that x0, df by dx is 0. Means that is a critical or extrema point. So that point can be maxima or minima. To find it, it is maxima or minima. We have df by dx at x equal to x0. That is a scalar I get. d2f, okay, so df by dx when x equal to x0, so that is anyway 0. Then I get another differentiation d2f by dx square at x equal to x0. Now gx, whatever we have written gx, this gx we take up to polynomial of power 2 only. Beyond that we don't take. So it is df by dx into x plus d2f by dx square into x square by factorial of 2. So df by dx is 0. So first term goes away. d2f by dx square into x square by factorial of 2. Okay. So d2 square f by dx square by factorial of 2 is coefficient of x square. That becomes equation of a parabola. So d2f by dx square by factorial of 2, whatever the sign is, that decides that extreme point, that is at x equal to x0. So d2f by dx square at x equal to x0, that is a scalar value, divided by factorial of 2. If it results in negative, then the point we are discussing x0, at that point the curve is maximum. If it is positive, the curve is minimal, because paraboloid, which is positive paraboloid, is minimal paraboloid. Negative paraboloid is maximal paraboloid. So this is how it is used for. Now question arises is, if this is the one case where we use this equation for finding the maxima or minima at point x0. Now other is, if I have equation of gx and gx is kind of approximation of fx, what about if I say df by dx into x plus d2f by dx square into x square by factorial 2, then it is considered that gx passes through origin. If it passes through a point x0, y0, then it comes in equation as gx equal to fx0. Means fx0 means at point x0, what is the vertical point? If this is x-axis and this is y-axis, then at x0, this is y0, then this curve passes through x0, y0. If that is the case, then gx equal to y0, means gx equal to fx0 plus df by dx into x minus x0 by factorial of 2 d2x by dx square into x minus x0 whole square by factorial of 2 plus like that dnf by dxn into x minus x0 to the power n divided by factorial of n. Okay, now This we proved through differentiation way. We took the differentiation for each power of polynomial. We reproduced it. So, like I took example of, like, if I have a polynomial of power 2 as fx, that is kx square, then, or kx to the power 3. If I take 3 derivative, then it becomes k into 3 into 2 into 1. Or if I just say just it is x to the power 3, then if I take triple differentiation, then it is 3 into 2. That's it. First it is 3x square, then 3 into 2x, then 3 into 2 into 1. That is factorial of 3. If I want to reproduce it as gx, then it is d3f by dx cube into x to the power 3. So d3x by dx cube is nothing but factorial of 3 into x cube. If I want to have only x cube, that is the reproduction, then I have to divide it by factorial of 3. So, exact replica of a polynomial of power 3, if fx is concerned, then gx is d3f by dx cube into x to the power 3 divided by factorial 3, because factorial 3 there I get when I do the differentiation. So we keep doing for monomial, binomial, trinomial, and keep reproducing as gx. Then we add everything and we get gx as complete polynomial approximation of fx. This is what we saw. Now, this is through differentiation, we proved it. Now I have to prove it through integration. So integration by part. Integration by part means if I have two functions fx, gx, and I have to integrate fx and gx, fx, gx, dx, and integration, then it comes as fx I have to keep outside and I have to integrate gx. So fx into integration of gx plus derivation of fx into integration of gx, whatever comes, integration again. So this is integration by part. Fx gx integration is fx integration of gx plus, minus fx integration of gx minus big integration. Inside that two terms. One is df by dx, means differentiation of first, that is f, and integration of gx again. So whatever comes, then big integration. So this is something called integration by part. If I have I have to calculate integration of two functions, they are multiplication, fx into gx. So now leave it. Now we have a term called fx. If I have fx, then fx can be written as fx0 plus fx minus fx0. fx0 plus fx minus fx0. Fx can be written like this. So fx0 will cut each other. It will remain at fx. So fx0 plus fx minus fx0, fx minus fx0 can be rewritten as integration from x0 to x. Integration from x0 to x. Okay. Integration of x0 to x of f dash t dt. df by dt into dt. If I write df by dt into dt, and if I do the integration, it comes as ft. Now if I set it the limit x0 to x, then it becomes fx minus fx0. So fx equal to fx0 plus fx minus fx0. Fx minus fx0, they cut each other and it becomes fx. So, fx equal to fx0 plus integration x0 to x f dash, means df by dt, f dash t into dt. So this is the converted form. Now if we see closely, f dash t into dt, I can change it to f dash t into 1 dt. So there are two functions now. One function is f dash t into 1. Please concentrate, because this explanation probably you don't get. This is not an invention, but this explanation probably you don't get. So the integration of f dash t, braces t, f is a function over t, f dash is a function over c. F dash t means df by dt. F dash single quote f dash t into 1 and then dt. So two terms, f dash t and 1. Now if I do integration by part, then f dash t I'll keep outside and then I'll integrate 1. Let's remove the limit, that is x0 to x. Just remove it. So f dash t and integration of 1 dt. So it comes as t. So f dash t into t. So this is what we are getting. Okay, f dash t into t minus big integration, and inside big integration we have first derivation. So f dash t becomes f dash dash t d to f by dt square. So f dash t becomes f dash dash t f single quote two times double differentiation f dash dash f quote single quote t into t, because I have to integrate 1, so it becomes t. Now this is second term is minus integration of f dash dash t into t d. Now that term if I integrate by part, then it will become f dash t. I have to keep it out, f dash dash t, and t I have to integrate as t square by 2. So it t square by 2 again minus. So this minus, anyway we had minus prior to it, so it becomes plus integration of f dash 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 f3t by dt cube into whatever integration we d for t, that becomes t square by 2 dt. So full term what we are getting is fx equal to fx0 plus f dash t into t minus integration of f minus f double dash t minus f double dash t t square by 2 plus integration of f triple single quote means f dash dash t into t square by 2 dt. It will keep on happening like this. This is integration by part. So we started with fx plus integration of f dash t into 1 dt. So integration by part means f dash t into t minus f double dash t into t integration. Now minus integration of f double dash t into t would result in again integration by part. So the first term would be f double dash t, I'll keep outside, and t dt. So f double dash t square by 2, and then minus, so minus plus, and then integration of f triple dash into t square by 2 dt integration, and it will keep on happening this way. So now we have term called fx equal to fx0 plus f dash t into t minus f double dash t into t square by 2 plus integration of f triple dash t into t square by 2 dt. Okay, now idea is that I have to use the limit, that is x0 to x. Okay, to use the limit, wherever I see t square by 2, something like that, that I will replace with a term that is called t minus x. Wherever I see t, I have to replace with t minus x. If it is t minus x, there is no change in integration, because if t equal to t minus x means dt equal to dt if I derive it. So there is no change in integration. But if I see t, it will be replaced by t minus x. Now I have to place the limit x0 to x. Now I would reiterate the whatever the formula I have received. Fx equal to fx0 plus f dash t means df by dt. F dash t function of t into t minus f double dash t into t square by 2 plus integration of f triple t into t square by 2 dt. Now, first fx0 plus f dash t into t. So t I'll replace with t minus x with limit I'll set it as x0 to x. If it t minus x and t if I replace with x, then it becomes 0, gone. Okay, and t minus x if I place, then it becomes 0. Now x lower limit x0 I have to place. So I'll put minus, because if I put lower limit I have to put minus, and then x0 minus x. So now the first term went away, forget it. F dash t, this explanation is not available anymore. F dash t, f dash t into t. T I replace with t minus x. If I replace with t minus x and then set limit from x0 to x, if I set x t as x, then x minus x, full terms become 0. Minus, then I have to substitute x0. So x0 minus x. So minus f dash t. Now t is x0. So minus f dash x minus f dash x0 into x0 minus x. If I remove this minus, then that becomes x0 minus x become x minus x0. Now first two term is fx0 plus f dash x0 into x minus x0. This is what we want. You remember that when we said that it passes through a point x0 y0, then we say that it is the equation is fx0, the gx equal to fx0, the first point, plus df by dx at x equal to x0. So it becomes fx0, okay, dfx0 into x minus x0 divided by 2, t square by 2. So divided by 2. Now, after that, we had minus f double dash t into t square by 2. So t square by 2 is now t minus x square by 2. So first is, now I have to place limit x0 to x. First x makes everything 0, x minus x whole square by 2. Next x0 comes. So before it was minus, it becomes plus. And then x0 minus x whole square. It is same as x minus x0 whole square. Now first three term is fx0 plus f dash f dash f dash x0 into x minus x0 plus, okay, there is no by 2. I'm sorry if I said that, plus f double dash x0 into x minus x0 whole square by factorial of 2. Okay, now beyond that, okay, I have plus and then integration of f 3 times f dash 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 into t square by 2. If I do this integration, then first I have to keep f dash 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 3 times outside and integration of t square by 2. That will become t to the power 3 by factorial of 3. T to the power. So I have f triple dash t into t to the power 3 by factorial of 3. Okay, and minus, okay, minus again integration of f 4 times dash t into t to the power 3 by factorial of 3. It is keep going like this. If f3, now the whatever I have, we have f3t, f dash 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 3 into t to the power 3 by 3 factorial of 3. If I replace t with t minus x and then place limit x0 to x, then x will make it complete 0. If I place x, okay, then minus x0 minus x to the power 3 by factorial of 3. So minus x0 x0 minus x to the power 3. If I make it x minus x0, the negative would come out. So negative will become positive. So first four term now is fx0 plus df by df by dx at x0, dfx by dx at x0, or we call it f single dash x0 into x minus x0 plus f double dash x0 into x minus x0 whole square by 2 plus f 3 times differentiation x0 into x minus x0 to the power 3 by factorial of 3 plus. Okay, so we proved it. Okay, so idea is that if we have a function fx and we want exact replica of fx in gx, if I have a function fx and we want exact replica of fx as gx, we also call polynomial approximation that gx is nothing but fx0, that is y0, plus f dash x at x0. I can say when we are trying to find the minima or maxima, at that time it becomes very clear, into d2 into x minus x0 plus f double differentiation into x minus x0 whole square by factorial of 2 into f triple differentiation into x to the x minus x0 to the power 3 by factorial of 3 plus f fourth differentiation, 4 order differentiation into x to the power 4 by factorial of 4 plus f nth time differentiation into x to the power n by factorial of n. Okay, so this is the idea of gx, polynomial equivalent of fx. Okay, anyway, more or less this proof is available anywhere else you can find. But idea is this way of clear explanation is not available anywhere. People would, the way they approach this is they would start that if I have fx g dash x, fx g dash x, and if I do integration by part, then it becomes fx gx minus f dash x and gx, then integration means, and then they will take the example t minus x to the power. First of all, you won't understand, but if you understand, then you can't demonstrate. So the idea of generating gx from the fx is first you calculate the derivative, the integration by part in the term of t1. So gx equal to fx0 plus integration of f dash t into 1 dt. Then like that you get everything in the term of t1, t square, t to the power 3, 3 means t square by factorial of 2, t to the power 3 by factorial of 3. Like that, keep getting. Now replace t with t minus x and place the limit from x0 to x. Keep doing it wherever you see minus. Okay, integration by part is first is f dash t and t, then minus f double dash t into t, then integration, like that. This is what we get. Whatever negative you are getting, you will get it as positive, because at the end we do x0 minus x. If I shift it x minus x0, then negative comes out and it makes everything positive. So, and the end integration by part, first get it into t and then replace t with t minus x and place limit from x0 to x1. Then whatever you have f dash t, f double dash t will convert into f dash x0, f double dash x0, f triple dash x0, and whatever you have t, that will get converted to x minus x0, and whatever you have as denominator, that will remain as factorial of 2, factorial of 3, factorial of 4. Wherever it is negative as the coefficient, that will become positive. So altogether it gx polynomial approximation of fx becomes fx0 plus dfx by dx at x equal to x0, that is f dash x0, into x minus x0 plus f double dash x0 into x minus x0 whole square by factorial 2 plus f triple dash x0 into x to the power 3 by factorial x minus x0 to the power 3 factorial of 3 plus then f to the power n, n order differentiation at x0 into x minus x0 to the power n by divided by factorial of n. What you want else? So simple. It's so simple that through kind of just from the voice only, the vocal demonstration, you can say that I demonstrated. Otherwise, pen paper is required or board is required. But if you use board, problem with the board is that 3D explanation what we are making. For each rotation of the 3D what I take, if I keep drawing then full day, 10-minute demonstration this way, it would become full day demonstration. So on board it is not possible. You are in multivariable calculus. So multivariable calculus has to be demonstrated in this fashion only. So that is the idea. Now by integration by part, we proved gx as fx. So what is remaining? This is singular, means independent variable is only one, that is x. X and fx, this is what it is. So fx to gx. What about fxy to gx? This is not available anywhere. Whatever explanation is there beyond anyone's thinking control. They do lot of imagination, delta x, delta here and there, and then some of forcibly try to do the find the find the gxy polynomial approximation of fxy to gxy. Anyway, through differential way, we have already proved it. Through differential way, we have already proved it in a sense that if I have a power of 2, that is uh, that is d to the power, means if I take power of 2, so dfxy, if I take in the power of 2, then what it is? So if I take a function fxy in the power of 2, then I can say it is x plus y whole square. X plus y whole square. That I'll also prove why I take x plus y. Then it comes as x square plus 2xy plus y square. If I want to replicate x square plus 2xy plus y square, that is fxy, exactly as gxy, then first I'll do dual differentiation with x. So fxx, that becomes 2. fyy, it becomes 2. And fxy, d of dy of dfxy dx, dual differentiation, that is fxy f and down xy fxy, then it becomes 2 again. Now I have d2 f by dx square, d2 f by dy square, and dy of df by dx, all as 2 2 2. If I want to exactly replicate it, then it has to be fxx into x square by factorial of 2 plus fxy into x into y plus fyy into y square by factorial of 2. Then it is exact replica of the polynomial fxy to the order of 2 in gxy. Similarly, I'll do for 1 power, 3 power and n power. Then if I add all together in gxy, then gxy as a full polynomial, it is full approximation as far as multivariate is concerned xy. This fundamental can be taken for the 3 variable, 4 variable also. So I started with x plus y whole square, then it will become x plus y plus z whole square, like that. Now, then if I add for first order, second order, third order, everything in dxy, then dxy is a new function, that is polynomial approximation of the fxy. So I proved it through differential equation. Now we will prove it through integration by part, and that is patentable. Okay, so we have found the solution. That is, so idea is not to do invention, that idea is not to place disclosure, because we have done differently. The idea is that whatever we have done, it should be much more simpler to, if it is anyway available somewhere. So somewhere the fx approximation at gx as far as multivariable is concerned, through integration by part or whatever it is, this proof is available, but it is too difficult. So we have placed that is equally easy, that is too difficult, here it is equally easy to implement and understand. So we will file this also, we will file as disclosure, because the way we have thought is different and there it is altogether different. So wherever difficulty is growing, our approach is going there and to make it equally easy. So fx approximation as polynomial gxy, fxy approximation as polynomial gxy, so that we will see.